Hello, this is Mr. Gilmore with the 5.3 Applications of the TEAI, ATT, and the Converse of ATT lesson. We're going to actually now pause and take a moment to actually use these first three theorems we've encountered into this chapter, of actually using them in some problems and in proof. What I'd like to do is review these three theorems, and then we're going to use them to actually justify why we know certain angles of certain types, and also use them to cross-compare angles and sides. Let's review the TEAI, the triangle exterior angle inequality. It says that the measure of the exterior angle is greater than either of its two remotes. In other words, in the diagram below, the measure angle 1 is greater than the measure angle 2, and the measure angle 1 is greater than the measure angle 3, because 1 is an exterior angle formed of the triangle, and 2 and 3 are its remote angles. We also have the anisosceles triangle theorem, or the ATT. It simply just says that if one side in a triangle is greater than another, then the angle opposite that greater side is the greater angle. So down below, if we have ABC, triangle ABC, such that AB is greater than BC, then the measure of angle C is got to be greater than the measure of angle A. It's opposite the greater side, thus it must be the greater angle. And the converse then is the exchange of that. If we then are given a comparison of two angles in a triangle, let's say the measure angle C is greater than measure A, then the side opposite of angle C must then be greater than the side opposite of angle A. So down below, AB would then be greater than BC because of the converse of the anisosceles triangle theorem. We can use these three theorems then to compare angles and compare sides within several different types of examples. Now, before we move into our first set of examples, I do want to throw two quick theorems at you. We should have proven these theorems already, but I do want to make sure I give these to you now. They're very simple. If you'd like to see the proof of them, I can show you them later. But here are the two quick theorems. The first one says, if two angles form a linear pair and one angle is obtuse, then the other is acute. And the second one says, if two angles form a linear pair and one angle is acute, then the other is obtuse. Now, I would really appreciate the help of naming these two theorems. I'm going to come up with QTO and QTA, respectively. The quick theorem obtuse and quick theorem acute. With quick theorem obtuse, it means we're given obtuse, we'll then conclude the angle is acute. And with quick theorem acute, that means we're given acute and we can prove the angle is obtuse. Now let's actually use the several theorems we've seen in the previous lessons, and the quick theorems I just threw at you, to actually then classify angles within this diagram. What I mean is, if I give you some angle information, you can actually label the angles as either obtuse, acute, right, or simply not enough information. Let's take a look at our diagram below. We've got a lot of information and a lot of angles. The first thing I want to give you is that the measure of angle 9 is equal to the measure of angle 10. In other words, if those two angles are actually equal, the triangle that they're in must be isosceles by the converse of the isosceles triangle theorem. And we prove that in all isosceles triangles, that the base angles must be acute. That was one of the tasty corollaries. So immediately we know that angle 9 and angle 10 are acute. Well, we can use one of those quick theorems I just threw at you. If you know two angles form a linear pair and one is acute, then the other must be obtuse. So I can then follow up by saying that angle 8 and angle 11 must be obtuse. Now, if we've got triangles that have obtuse angles in them, back in our chapter 4, in one of those tasty corollaries, we proved that in an obtuse triangle that has precisely one obtuse angle and the others must be acute. So then immediately following, I can then say that angle 6, angle 7, angle 3, and angle 4 are all acute angles. What then follows? Well, then our quick theorem acute, if angle 7 is acute, then angle 13 must be obtuse. Using vertical angles theorem, I can say 14 is obtuse, and also I can say angle 12 is acute by vertical angles theorem. What we're left with is angle 1, 2, and 5. We simply don't have enough information. Just because my triangle is isosceles in the middle doesn't make angle 5 any particular angle. It could be acute, right, or obtuse, and you can't base it on what it looks like. So this would simply be not enough information. Angle 1 and angle 2, I know that they form linear pairs with some of these angles. However, with angle 5 not being in any information that we can actually get, with not being a specific classification, angle 2 and angle 1 are also left out of this mix of being not enough information. And again, we can't say that they are obtuse because they look like it. We have to actually have concrete evidence that they are. Let's use that same diagram but for a different story. Let's actually use the triangle exterior angle inequality to then satisfy a certain condition. So in this, you're actually listing out angles that satisfy this certain condition. For example, again in our diagram, let's take a look at angle 7. I want to find every single angle that is greater than angle 7. So here's our angle 7. Now again, I've taken away what we knew last time. We don't know angle 9 and angle 10 are equal this time, but we do know some information. If we take a look at the triangle that's angle 7 is formed in, with the three angles, 6, 8, and 7, angle 9 is an exterior angle, which means we can claim that angle 9 is definitely in that list of being an angle greater. Why? Because it's an exterior angle and 7 is remote. I can continue that process if I look around my triangle. I know then that angle 11 is exterior, so angle 11 is definitely in that list as well. And I actually see one more angle. In that triangle there, if I extend out this side, that means angle 2 is a remote angle, or exterior angle, and 7 is remote, so angle 2 is definitely in there. Now, I do think, it does appear that angle 1 and angle 2 are vertical, but they're not quite. If you take a look at the two sides, they're kinked, right? They don't form two lines. So angle 1 I can't throw in there. But I could definitely claim angle 9, angle 11, and angle 2 are greater than angle 7. Out of all the other angles, I'm not quite sure, right? There's nothing else that I can actually use as concrete evidence to say that angle 9, 11, and 2. And actually, now that I think about it, if I think about the triangle with angle 9 in it, angle 1 is actually an exterior angle to that triangle. So in other words, angle 1 is greater than angle 9, and since angle 9 is greater than angle 11, hey, I can actually throw angle 1 in there. That's actually a fun discovery. So actually, those four angles are definitely going to be greater than angle 7. Let's do this same diagram, but a different category. So a similar example, but I'm going to change the category. Now I want to find all the angles that are less than the measure of angle 13. So angle 13 is already given to us as being exterior, and is exterior to a lot of triangles. If we take a look at the first triangle here, which is actually the triangle that contains angles 6, 7, and 8, I know I have two remote angles there to angle 13. So angle 6 and angle 8 definitely got to be less than. What are some other ones? Well, if I continue out that triangle, I've got this other triangle, which means I can throw in angle 5 and angle 10. Those are going to be less than 13 because if you think about angle 5 as part of this entire angle, and since it's part of it, it must then be less than 13 is going to be greater than that entire angle, which means 5 is definitely going to be less than that one. So 13 is definitely greater than angle 5. And I can extend out the triangle again, and we have here we have angle 3 and angle 4 thrown into the mix as well as being angle 13 is less than that. Out of everything else that we know, though, that's about all that we're going to be able to claim. I can't claim angle 13 is greater than 12 because it looks like it, and I can't claim that angle 13 is greater than 7 because it looks like it. I don't know what the measure of angle 13 is. I can't just base it on what it looks like. But I can guarantee that those six angles, 6, 8, 10, 5, 3, and 4, are definitely going to be less than 13 because of the triangle exterior angle inequality. That's usually what we're see when we use that in our comparisons with these angles in the category lesson here. Now let's actually move into some proofs. Let's use what we know about our exterior angles and our cross comparisons of sides and angles to actually prove things to be true. So in the diagram, we have this triangle ABC, and actually a larger triangle ABD, such that AB is equal to BC, and then which is also equal to CD. We're going to prove that the measure of angle 1 is greater than the measure of angle 2. So here's where I like to start in my proof. The first thing I like to do, obviously, is I get my given. And then what I begin to do is realize what kind of angles certain angles are. So for example, if you take a look at angle 1 is actually an exterior angle to this isosceles triangle here. If I label my base angles of my isosceles, angle 3 and angle 4, I can actually say, okay, by the ITT, I know that angle 3 and angle 4 have got to be equal to each other. You're going to see that that's going to be important here in just a second. Because I can claim the measure of angle 1 is got to be greater than the measure of angle 3 because of the triangle exterior angle inequality. But notice that angle 4 is an exterior angle to this triangle, triangle BCD. So at the same time, I can claim that measure angle 4 is greater than the measure of angle 2 by the same reason. What can I do with that? Well, if I know measure angle 1 is greater than angle 3, and angle 3 is equal to angle 4, then by a quick bout of substitution, I can claim the measure angle 1 is greater than the measure angle 4 because of substitution. Take angle 3 out and plus angle 4 in. Now take a look at these previous two statements. If angle 1 is greater than angle 4, and angle 4 is greater than angle 2, then I can conclude that angle 1 has got to be greater than angle 2, and that is by the transitivity of greater than. There's a couple of different ways that I've seen this proof handled. This is the way that I like to do it, using that triangle exterior angle inequality and with our transitivity of greater than. Let's take a look at another example using our triangle exterior angle equality and also using some of our other theorems to justify that in our diagram here, we're going to be able to prove that angle ABC is obtuse. So let me go ahead and mark where ABC is. This is where this angle right here. So in our given, we're told that BD is equal to CE and that BC is congruent or equal to DE. And also that angle E is acute. Let's prove that angle ABC is obtuse. Here's what my proof is going to look like. First of all, I've got my given, so I'm going to restate my given. BD is equal to CE. I've got BC is equal to DE. And I've also got angle E is acute. So given. Now, if you notice that BD and CE and BC and DE, that's actually two sides of one triangle equal to two sides of another. And you'll notice that those two triangles share a side. So CD is definitely equal to itself. I can claim that by reflexivity of equality, which then leads me to triangle congruence. Triangle BDC is congruent to triangle ECD by side-side-side congruence. Now, why is that important? That's because I can then claim the measure of angle E is equal to the measure of angle B by CPCTC. Now, if angle E is given to us acute, that means I can also now claim that angle B is acute because I should actually do this. I should say not angle E and angle B. I should say angle E is equal to the measure of angle DBC. There we go. That's more appropriate. I can then also claim that angle DBC there is acute. Why? Because everything true about angle E is also true about angle DBC, and that's by substitution. So what is then important about knowing that angle DBC is acute? That means if two angles form a linear pair and one of them is acute, the other must be obtuse. So if we take a look here at step 6, I can say that angle ABC is obtuse by one of those quick theorems. That would actually be quick theorem acute, because if we're given that one of the linear pair angles is acute, then the other one must be obtuse. And there we have it, the end of our proof. So using, right, we can use actually congruence in this one, we use CPCTC, we use that quick theorem, we actually can arrive to the conclusion of comparing our angles and actually knowing what our angle relationships are. Let's then finish off our lesson with just two additional properties that I want to give you. Let's talk about the addition of unequals. Let's say, for example, that you have four quantities, A, B, C, and D. If I tell you that A is equal to B, but that C is greater than D, if I add unequal things to both sides, then I'm going to result in unequal things. So in other words, if I took A plus C and B plus D, I get that A plus C is greater than B plus D. Here's a quick example. If 7 is equal to 7 and 10 is greater than 2, then add the unequals to both sides. 7 plus 10 is definitely going to be greater than 7 plus 2 because I get 17 is greater than 9. And then we end off our chapter, or with this lesson, with subtraction of unequals. Think about this. If I have four quantities, A, B, C, D, and again A is equal to B, and C is greater than D, what if I took C away from A and took D away from B? Well, if I took C away from A, I'm taking more away than I'm taking away from B. So that, in other words, I'm saying that A minus C is less than B minus D. Here's a quick example. If 12 is equal to 12 and 7 is greater than 3, then 12 minus 7 is got to be less than 12 minus 3, or rather, 5 is less than 9. You are definitely going to use the subtraction of unequals on your homework assignment tonight. As you jump into that, you're going to see several examples of using the TEAI, the anti-isosceles triangle theorem, the converse of anti-isosceles triangle theorem, and you're going to see that in proof as well. If you do have any questions on the 5.3 worksheet, do not hesitate to email me. With that, be good and do good.